Okay, good afternoon and welcome to the webinar Electromagnetic Interference and Considerations for Transit, hosted by the Ontario Society of Professional Engineers in partnership with Accio. OSPE is the voice of the engineering profession in Ontario. We represent the entire engineering community, including professional engineers, engineering graduates, and students who work or will work in several of the most strategic and influential sectors of Ontario's economy. Our partner for today's event is Accio Consulting. Accio is a management and technical consultancy firm focused on electrification of transportation and smart grids. Accio has two subsidiaries, C3 Plan and Cyan Wall, which are focused on cybersecurity. Please reach out to Felipe Sarabi if you have any inquiries. For today's webinar, we will start off with a presentation from Professor Razai Zare. Professor Razai Zare is an associate professor in the Department of Electrical Engineering and Computer Science at York University. Prior to joining York University, he was with Hydro One Networks in Toronto, working in the departments of Special Studies, Transmission System Planning, and Transmission Reliability and Performance Analytics. After the presentation, we will move to a panel discussion with representatives from Network Rail, Metrolinx, Gannett Fleming, and Infraspeed, moderated by Marco D'Angelo, who is the president and CEO of CUDA. As president, he has continued to position CUDA as Canada's voice for public transport, transit, and urban mobility. Throughout his last year, D'Angelo mobilized the CUDA team, consulted with transit systems across the country, and tirelessly advocated for emergency support for transit. Not only advocating, but succeeding in securing an unprecedented $4.6 billion in emergency operating support. Before we begin today, I'd like to go over some housekeeping rules as well. As an attendee, you're in listen-only mode. If you'd like to make a comment, please use the chat feature on the right-hand side of your screen. For any questions that you'd like the panel to consider, please use the question box that can be accessed on the bottom of your screen. I now give the floor to Professor Razai Zare.
Hello, everyone. Thank you very much for the introduction, and let's start with the presentation on basically the effect of electromagnetic field exposure and interference on the electrified transportation system. Well, this is just the introductory presentation on this without going to too much detail. Let's start with the fundamentals of electromagnetic field, because here we are dealing with this field. So let's start with the different types of that and how they can be generated, etc. So as obvious from the name, electromagnetic field is basically has two parts. So electric field and magnetic field. Electric field is generated by two, let's say, opposite charges, for instance, as shown here. When there are these two opposite charges, there is a voltage difference between the two, and whenever we have a potential difference on voltage between two, let's say, points, we have electric field. And the electric field is basically somewhat proportional, at least depends on the voltage. So with higher voltage, we have higher electric field. On the other hand, for magnetic field, in the simplest form, the magnetic field can be generated by a permanent magnet, as you know. So a permanent magnet around it, we have a magnetic field going from N pole to the S pole. But in electrical systems, typically the magnetic field is generated by electrical current. So electric current flowing in a wire, let's say like this, based on the rules in electromagnetic, it generates a magnetic field around it. The direction of that is given by the right-hand rule. When the thumb is pointing to the direction of the current, the fingers basically show the direction of the magnetic field around that wire. But the important point here is that B, or the magnetic field, is depending on the magnitude of the current. So higher current means higher magnetic field. So this is the takeaway from these two slides, is that the magnetic field depends on the current. Electric field depends on the voltage. So these two considerations are important for later discussion. Now, When we have in electrical system, definitely we have both voltage and current at the same time. So we have magnetic field and electric field coexist together, and basically they join and combine each other and form the electromagnetic wave, like what you see here. So the blue wave is the electric field, and the red one is the magnetic field with 90% spatial phase shift. Basically, they combine to each other and propagate in the space with the speed of light. So here we are dealing with the combined one, electromagnetic wave. And this is just a very simple example when we have a table lamp, for instance, on the left side, assume this is plugged in, but it still is not turned on. In this case, the wire gets voltage, and due to the voltage, around the wire, we have electric field, but there is still no current, so there is no magnetic field. Only electric field exists in this case. Electric field is measured in volts per meter. And for, let's say, a larger unit, we use kilovolt per meter. The electric field can be easily shielded or weakened by conducting objects such as trees, buildings, and any kind of metals. And the strength decreases rapidly with increasing distance from the source, which is a good point for, at least for EMF exposure, the topic that we discussed today. On the other hand, for magnetic field, when we turn on the lamp, we have current in addition to the voltage. So in addition to the electric field, we have magnetic field around that, showing by these basically red arrows and circles. Magnetic field measured in Gauss or Tesla. This is the unit. Gauss is a smaller unit for the magnetic field. And but the problem with magnetic field is that it's not easily shielded or weakened by most material. But the good point is that the strength again decreases rapidly with increasing distance from the source. So having said this, for instance, look at the example, another simple example here for a printer. So this printer has definitely a magnetic field around that because it uses current, electric current. So next to the printer, we have in 6-inch away, we have 90 milligauss intensity of the magnetic field. But as we go further, sorry, from the printer, the magnitude of this magnetic field drops quickly. So 90 in 1 feet, 20 in 2 feet, 7. So you see from 1 feet to 2 feet, we have the ratio of almost three times weaker. And when we go to 4 feet away, it's almost gone. So from 90, it decreased to 1 milligauss. So this is one clear example that how fast the magnetic field drops based on the distance from that object. Here we are dealing with basically 3 important definitions. So first, starting with the electromagnetic field or EMF, we already discussed and explained what the electromagnetic field means. But the next one is electromagnetic interference. So the interference is defined as a disturbance generated by an external source that adversely affects an electrical circuit by electromagnetic induction. These are the 3 ways that EMI can be transferred, let's say, and applied to the other equipment. This is either electromagnetic induction or electrostatic coupling or conduction. These are the 3 ways that EMI is transferred and applied. And the EMI, both man-made and natural sources, generate changing electrical currents and voltage that can cause EMI. So some examples are these: ignition systems, cellular network of mobile phones, lightning, solar flares, and a storm, and aurora or northern lights. And finally, we are dealing with electromagnetic compatibility, which is very important, and we need to comply with this. EMC is the ability of electrical equipment and systems to function properly in their operating environment by limiting the unintentional generation, propagation, and reception of electromagnetic energy, which may cause unwanted effects such as electromagnetic interference or even physical damage in operational equipment. The goal of EMC is the correct operation of different equipment in a common electromagnetic environment. So the goal is that when we have multiple electrical equipment operating next to each other, we have to ensure that they are not influencing the operation of each other adversely and cause maloperation in the other equipment. So this is the meaning of EMC. So having said this, let's start with the EMI in railway systems. So what are these EMI? First of all, why EMI is important in electrified railway system? First of all, we want to move toward the electrified transportation because the future of all sorts of transportation is going toward more and more electrical. So today, for instance, we are dealing with electric cars. So the combustion engine car is converted to electric cars. Also today, we are talking about electric plane, electric boat, ship, and in the same way, we are also talking about electric transportation. And this is why, because we can have access to unlimited green and sustainable energy from basically renewable energy resources like wind and solar. So, and that they are green and no or zero emission, let's say, energy sources. And on the other hand, for the electrified transportation system, we are dealing with these issues, let's say. So we have increased traffic flow. We need higher speed trains these days because they are in relatively, let's say, short distances, a few hundred kilometers. Now the higher speed trains is a good candidate to replace even planes. And so this is the need. More trains per hour is needed. Longer trains and heavier axle loads are needed, basically. And all of these are translated to more powerful engines. We need more powerful engines. It means in electrified systems, we need to draw higher power from the grid. And the higher power in turn is translated to higher current and higher voltage. And as we discussed before, higher voltage, higher current means higher electromagnetic field. And so the EMI in future transportation system is more and more important than today. So in addition to that, in railway systems, the number of electronic equipment is increasing. So more electronic systems means we have more vulnerability and high sensitivity to EMI for these new systems. And on the other hand, the statistics in electrified railway systems show that 70% of all faults can be caused by EMI. So this is why EMI is very important and is not the thing that we can ignore for modern systems. Now, if we look at just very typical electrified railway system, we are dealing here with 4 different electrical systems. First of all, we need the power grid to supply our railway system. So here we are dealing with power grid. So we have transmission power grid here with the voltage and current. So it itself generates the electromagnetic field around that. And for instance, in this picture, in parallel with the track, the power lines are running. And this one, in close vicinity, they can highly influence and induce electromagnetic field in basically a railway system. So here, the electrical system number 1 is power grid itself. Then it supplies the substation feeding the railway system. So the railway system itself has voltage and current because this is electrical system number 2. So it has its own electromagnetic field generated. Electric system number 3 here is the train itself. The electric train is a moving power system itself. And it has the power converter, electric motor, even the signaling and communication systems, all electrical systems. And finally, the electrical system number 4 is the signaling system next to the tracks and the railway system. So here in general, we are dealing with four electrical systems interacting each other. And if you compare, for instance, with the conventional railway system, the train is not electrified, but the signaling system is anyway electrical system. Still, we have some interactions with the control systems of the train itself, with signaling, etc. Now, add more complexity to that for electrified system. Now we have four power systems or electrical systems interacting each other. This is why EMI again is very important in these electrified systems. And if we want to, let's say, split the different type of EMF, EMI, we can categorize these into two main groups. First of all is because of the supply, we have EMF, EMI from power frequency and basically power frequency voltage current, which highly depends on the train operation. Because train operation determines the value and the magnitude of the current drawn from that grid, and the value of current determines the magnetic field. That one results from the current flowing in the tracking power distribution system, as I said, through an overhead catenary system, electrified third rail, or rails themselves. On the other hand, we have also radio frequency EMF and EMI. A variety of communications, data transmission, and monitoring systems, both on board and off board, can produce radio frequency EMF. So these two are two main sources of this EMF. For 60 Hz, the power frequency group, as I said, that emission and interference depends on the train operation. And train operation contributes to EMF, EMI through the electric traction, overhead catenary system, and type of rolling stock. On the other hand, for 60 Hz, we define two different interference. One of them is the maximum steady state, the other one maximum short duration. For a steady state one, we basically determine this based on the worst condition. And the worst condition from train operation point of view is that how many trains they start and stop together. So the maximum is to occur when a maximum number of trains accelerate or decelerate simultaneously. And this one determines the magnitude of current, which is injected or drawn from the grid. And therefore, magnitude of current determines the magnetic field intensity. On the other hand, for the short term, we have also short-term interference. That one is typically of short duration nature, and they are infrequent. And that one results during a malfunctioning in the electric traction system, such as short circuit. For instance, if we have short circuit between the main contact wire and the feeder return, for instance, in the auto transformer configuration, we have some kiloamps current for a short term. This is short term, but due to high magnitude kiloamps current, we cannot just simply ignore it because of the high magnitude, and we need to take into account that situation. The maximum duration of this depends on how fast the protection system operates. So definitely we have protection relays protecting the electrical system. So how fast they react to the fault and clear the fault basically determines the duration of that short-term interference. These are just some of not many but more EMI incidents have reported in the past, and these are just some of them. Of course, these are known issues and there are solutions for this, but sometimes the problem is not that easy and it's really challenging to solve. So let's review a few of them to at least have a sense of what the EMI does with the electrified railway. So it can cause sudden re-energization. Well, this is one case, sudden re-energization of the train during transition from insulated to energized section of the basically electrical wire supplying circuit. That one creates a shock, a current shock, because when it moves from insulation to energized section, it suddenly draws that current, high current, let's say during the acceleration of the train. So it results in intensive emergency in one case that's reported, for instance, intensive emergency stopped due to EMI in signaling system and false red light. So right in front of the train, there was a light, it changed to red right away, and it caused, and this is false, of course, red light. It resulted in intensive emergency stop, and it was repeated a few times per week, day event. The second, for instance, example could be automatic train control, radio interface on track switch detectors. So, for instance, in one case could be something like this. So it caused wrong left or right for rail switch position detector due to interference signal from the ATC transmitter of passing train. So passing train caused that interference with this position detector switch. And EMI also can cause false signals in detector systems, such as indicating passing axles and reporting trains that did not exist. Or it can give a false alarm for a system down, while this is not the case, for instance. So these are just some examples. Now, so far we discussed the EMI. EMI will be applied and discussed from the electrical equipment point of view. These are affected operational electrical systems, let's say, and equipment. But here we want to talk about electromagnetic field exposure. And the exposure means the exposure on the humans and animals in terms of the intensity and the health hazard that it may create. So this is important to take a look. And first, let's start with the limit to see what is the exposure limit we can have, at least without problem, health issues. So first of all, we need to again split the type of radiations, electromagnetic fields, into two main categories: non-ionizing and ionizing one. So non-ionizing one, which is basically starting from visible light to the left, these ones are dealing with relatively low frequency radiations and electromagnetic field. While for the right-hand side, we are dealing with the high frequency one, extremely high frequency, more than visible light. So for the left side, which is non-ionizing, low-level radiation, which is generally perceived as harmless to humans, that these radiations are considered harmless. On the other hand, ionizing one, high-level radiation, which has the potential for cellular and DNA damage. So they include UV, X-ray, radioactive radiation, and we know that they are dangerous and they can cause problems in the body. So we are here and discussing, at least in these systems, if this is electrified system, etc., we are dealing with non-ionizing waves. And we have two important references for at least obtaining this exposure limit. One of them is ICNIRP, which is International Commission on Non-Ionizing Radiation Protection, is an organization of 15,000 scientists from 40 nations who specialize in radiation protection. So these values are coming from their 1998 document, and they have updated one. And the second group and reference is basically this ACGIH, which is American Conference of Governmental Industrial Hygiene. And so if you look at the limits that they provide, the safe limits, they are different first. But for the safe side, we can take, of course, the minimum among the two or three more values given here. We can take the minimum of that. And they typically provide the two main exposure. One of them is occupational exposure and general public. Occupational means the work condition of a worker when the worker does the assigned basically duty and job activities. Basically, that worker will be exposed to occupational exposure, because workers are supposed at least to wear suitable PPE, personal protection equipment. So they can be exposed to higher level field than the general public. General public means just, for instance, you are walking in the park next to a power line or under a power line. And so the general public exposure will be applied in that case. And as you see here, typically general public exposure is lower than occupational. So for electric field, we have these limits, 8.3, 4.2 kilovolt per meter, and magnetic field is 4.2 Gauss and 0.833 Gauss. And if you compare with the values provided by ACGIH, you see that the values here is 25, for instance, occupational exposure, 25 compared to 8.3. So this one is lower. We can take this, for instance, for more safety. So they say these values are safe. And the magnetic field is 4.2 goes to 10 Gauss, for instance, for ACGIH. But all of these information are based on, again, studies, research, and new investigations. This is why they typically update these documents. And this is at least the updated table for the IC nerve. In the new document, which is 2010, compared with the previous one that it was 1998, we have this table, which is very important and useful. It provides, for instance, on left, we have occupational exposure, for the right side, general public exposure. And if you look at this is frequency dependent. So based on what frequency range we are looking for, we can find the limit of that. For instance, for 6 years that we are looking for in this range, the electric field is given kilovolt per meter is given as this, which is obtained as the previous value. So there is no update in the, or at least the same value for the electric field, but in terms of magnetic field, previously it was 4.2, now it increased to 10 Gauss. So the new findings saying that the higher field up to 10 Gauss is still okay without any problem. And for the general public exposure, we have this. So again, for 60 Hertz, E field doesn't change, but the magnetic field is increasing from 0.8 to 2 Gauss. So this one is the new limit value. But one important observation here is that, as you see here, this is frequency dependent. So it means if we start, let's say, with very low frequency, for simplicity, assume we have 1 Hertz, for instance, close to DC. So the magnetic field level, the maximum permissible level is 0.2, means 200 Gauss, 200 millitesla. And compare with 1 millitesla in 6 years. So 200 millitesla drops to 1 millitesla for 6 years. So you see the effect of frequency. As the frequency goes high, this limit drops. And for instance, if we go to megahertz range, basically the limit, 1 order of magnitude drops. And if you are, for instance, interested to see what happens for cellular and cell phones, for instance, the cell phone is in the range of gigahertz. And if we accept this trend continues beyond this frequency range, we expect that this level will be, let's say, another order of magnitude lower. So you see that if you, for instance, compare the cellular radiation and exposure, consider the distance, which is basically 0, because this is in close contact with your head and brain. Also, if it's in your pocket, it's in direct contact with the body, basically. And in that sense, the cellular, even Wi-Fi modem at home, and Bluetooth from your laptop, etc., all of them are gigahertz range. So, and we are in very close contact with them. The bottom line is that if you compare, let's say, the 60 Hertz radiation, it's not worse than, let's say, cellular, basically, systems. And on the other hand, we have some recommendations in terms of the health issues from World Health Organization, or WHO. In terms of chronic, let's say, effects, the limit is 3 to 4 milligauss. So we should ensure that for every day, chronic exposure means every day for 8 hours or more exposure to 3 to 4 milligauss and higher than this, power frequency magnetic field exposure can pose some risk and it should be avoided. But these WHO studies and recommendations continue that for the other health effects, sufficient evidence shows that the EMF does not cause other health concerns such as cardiovascular disease or breast cancer. And more risks are also were studied, and including cancers in both children, adults, depression, suicide, reproduction, dysfunction, developmental disorders, immunological modification, and neurological disease. And the conclusion was that much weaker relationship was found corresponding to EMF. So other factors are more important and influential to create these diseases rather than EMF. And now let's look at a typical railway system and the magnitude of this exposure, etc. in that. So if we just review quickly the different systems in Europe, we have different AC versus DC voltage levels in the Europe, and in North America is mainly AC. In Europe, we have low voltage DC, high voltage AC, and this one is one of the most preferred configuration for electrified railway, which is called auto transformer configuration or system. In this system, at least in terms of both technical operation and EMF exposure and EMI, this configuration is better than the rest. For the main basically supply, we have a transformer center tap supplying the electrified system from power grid. And instead of, let's say in this case, instead of having full 50 kilovolt voltage, this configuration split the voltage into two halves. And so we have plus minus 25 kV instead of 150 kV. And when we have half of the voltage, we have half of the electric field, and EMF is half. So it's better in terms of exposure. And in this system, we have auto transformers in middle here to equalize the distribution of current. As a result, you see that if the full current of, let's say, 100 amps is drawn by the train, just some fraction of that goes through the wires. So this is 75%, this is just a quarter, and this one another quarter going to the main catenary and feeder, basically conductors. And these low and equalized current with the opposite direction, for instance, in this case, they can cancel each other, the field that they can generate. This one is shown here. So if we have two conductors, let's say, with the opposite current, the opposite current create opposite magnetic field around it. And due to the opposite direction, they somewhat cancel the effect of each other here. And for far fields, for instance, for a person here or signaling cables, etc., they see at least or experience very low magnitude of the interference. And this is another basically at least more detailed picture showing that for instance, in the configuration of the main feeder and the main contact wire here, we have this configuration and these distances for a person basically standing next to it. Again, the good point about this configuration is that we have two opposite polarity voltage. They cancel the effect of each other. Also, the opposite direction for the current flowing in these wires. And they also cancel the effect of each other, means the current cancels the magnetic field and the voltage cancels the electric field. And if, let's say, we calculate the electromagnetic field in this case, this is calculated by, at York University, we have in-house developed a tool to calculate these electromagnetic field exposures and magnitudes of any system, including the electrified railways. And in here, you see that, for instance, the orange one is the electric field, the blue one is magnetic field. And for a two rail, two tracks systems from the center of that configuration, going to the right or left, we see that the electric field drops quickly. So from a maximum, it drops within, let's say, 5-6 only meter from the center, which means the one track should be around here. So very close to that track, the electric field drops quickly. The magnetic field drops just slowly, but still after 10 meters, 11, 12 meters, it drops well below a safe limit. So 4 milligauss, 3 milligauss is very close again to the track, and it drops very fast. And these are some measurements to show the magnitude that we expect in the electrified system. This is a measurement done in US electrified system. So we are dealing with very low microtesla measurements for these conditions with this frequency range. These are well below the maximum permissible limit. And the electric field also, basically they are in the, the limit should be in kilowatt per meter, but you see this is only 52, for instance, volt per meter, is very low. And so we don't expect serious concern in electrified railway systems based on the measurements. If you, of course, the more measurements are available, if you refer to the link that I provided here, you can see and read more measurements in different conditions in different countries. Whenever we see the field EMF is going to be high and be a concern, for instance, we have some ways to mitigate that and control that field. One of them is modifying of the electrical feeder system, because the configuration effect, as we discussed, if they are canceling each other, they are close to each other, so they can have canceling effects. So we can control the magnitude of field. We need also, or we can consider voltage level. Voltage level directly affect the electric field. By controlling voltage, we are controlling the electric field. Positioning of the overhead catenary system wires and traction power substation, again, result in the different distribution of the current. And that one affect the magnetic field distribution. Changes to operation, again, is obvious that if we have different scheduling for trains, for instance, so the amount of the current drawn by those trains will be changed, and it affects the final magnetic field. And finally, we can shield or filter some EMI exposure and basically sources. This is one example of that, which is done in Germany, in Berlin. So in one station, this is the configuration of that tunnel and the station. And before controlling the electromagnetic field, the distribution of the field was something like this. So it goes well beyond the station. But with controlling and shielding the station, the magnetic field is confined to the space inside the station, as you see here. And it's not affecting the outer, let's say, buildings or persons, etc. And this is another station with this configuration, with this structure for electrified one, etc. Again, without shield, we have very large distribution and the space of the electromagnetic field exposure. But that one is limited after shielding to the space inside the station. And except this side, we have no external exposure, so it's not affecting the other buildings, persons, offices, etc. And these are just a very quick, let's say, overview of the issue of the electromagnetic field and interference in electrified systems. Thank you for your attention. Okay, back to you, John.
Thank you so much, Professor Rezaei. I'll now give the floor to our moderator, Marco D'Angelo, if you'd like to begin your introductions.
Of course, good morning, and thank you for that presentation, Professor. It really sets the frame here for the panel discussion that we're about to undertake over the next while until we reach 11:30 a.m. Eastern. And so let me first introduce today's panel. With us, we have Helen Yu. She's Principal Engineer for EMC in the Chief Engineers Team, Technical Authority at Network Rail. And she has a PhD in Electrical Engineering from the University of Strathclyde in the UK. She joined Network Rail in 2005 and has been lead engineer for EMC since January 2016. Andy Gillespie is a PN, Senior Vice President with over 30 years of experience at Gannett Fleming. And so he's worked on projects that included program development and management of both large and small electric traction projects, including Metrolinx's GO Transit Regional Express Rail System. And before Gannett Fleming, Andy was the chief engineer at Southeastern Pennsylvania Transit Authority, where he oversaw the 100% electric regional rail systems, as well as subways, LRT, streetcar, and bus infrastructure. Joining us as well, Menno van Limburg. He has been the EAM Director of Electrification at Metrolinx, right here in the Greater Toronto area. Since June 2017, he has 23 years experience in rail, heavy civil construction, and rail engineering projects across Canada, the United States, New Zealand, and the Netherlands. So welcome. And finally, Ad Hertogs, and he's been the operations manager for Infraspeed for the last 8 years, and is now Chief Technology Officer for the company. He's been working on railway projects in consulting, design, testing, certification, maintenance, and asset management. So he's also a civil engineer as well, and he's joining us today from Rotterdam, Netherlands. Okay, so with those introductions out of the way, welcome panel, and we're going to dive right in here, and we'll get to questions that have been prepared to really build on the opening presentation that we just heard. So first, let's go to Menno. Could you please provide us with a quick overview of the GO electrification program, as well as how your experience so far has been in terms of EMI?
Good morning. Thank you, Marco, for that introduction. So I'm Menno van Limburg at Metrolinx, as Marco has just outlined. Metrolinx, the GO electrification program is part of the overall GO expansion program.
Hang on. Okay, there was some echo on the line. We may have others that are unmuted. If everyone could mute except Menno, that'll be most helpful. Okay, sorry about that, Menno.
Can you hear me now?
It's a bit of an echo, but let's proceed.
Okay. Thank you. The GO electrification program is part of the GO expansion program, which you may be familiar. Metrolinx is programming a plan to transform the GO commuter rail into a backbone of the rapid transit network that will link up LRTs to connect people and communities across the GTHA. In November 2018, Metrolinx published the full business case for the GO expansion program, which demonstrates the economic and financial case benefits of implementing electrification on the GO network. As part of the development program, we have developed what we refer to as the reference concept design to deliver the service expansion requirements that we have under the GO expansion program. And this is to implement electrification on all Metrolinx own rail corridors, which comprises 600 kilometers of track throughout the area. The GO expansion business case demonstrates that this technology realizes a benefit cost ratio of 2.6 when operating electric vehicles compared to maintaining the current diesel-electric fleet. The extensive analysis and mitigation overview has been undertaken to assess and address the vertical clearance challenges and overhead structures, the 75 plus bridges and adjacent infrastructure that has been assessed, including an effort, an assessment of mitigation measures to address safety risks by means of installation of safety barriers and the like in areas where there is OCS proximity risk. With regards to EMI, a structured assessment of adjacent infrastructure and properties has been undertaken in, for instance, the USRC, and areas, the area that we would refer to as the station shed, the UP Express station in the airport link structure against the overhead line contact line zone area of impact and the mechanical and clearances, electrical clearance requirements.
Sorry, we'll just take a little pause there. You may have your volume up or your speakers are up, but it's a double echo from your end. We are catching it. It's just a little bit difficult to hear. Did you want to? I can come back to you if you like with the next question.
Yes, please do that, Marco. Thank you.
We'll do that. Okay. All right. And thank you.
So, Marco,
yes.
Just one comment. I think you're logged in twice. You also have your phone. I think that could be the reason.
Okay. Perhaps it's a double login on the cell phone. Okay. We will come back to Menno. Sorry about that. Okay. Let's go over to Andy here. As the engineering company supporting Metrolinx through this journey, what are some of the typical interfaces that you consider when you're designing systems in general and in the Canadian context?
There's a couple aspects, particularly in this subject matter. As Menno was mentioning earlier, versus clearances, how close are we bringing the electrification system to infrastructure that both crosses under and over the railroad, as well as the apparatus that may be located along the railroad. And one example is going up to the airport in Toronto. The advent of bringing electric trains into the airport needs to be considered against the impacts you may have on both the airport's operations as well as Nav Canada's control over the airspace above the Pearson Airport. So those become probably the two that biggest from the subject of this subject. There's plenty of other items that have to be addressed when considering electrification, the least of which is not the adjacent utilities, whether they be in the railroad, so railroads are used a lot of times for utility transportation, fiber optic cables as an example, to utilities that cross over the railroad, and how much space there will be now between those utilities and the railroad and the addition of the electrification equipment. So that becomes probably the two biggest items that we need to consider when we're talking about electrification.
There we go. Okay. That mute button got very hard to find for a second. Excuse me. Thank you. Okay. Thank you for that answer. So we talked a bit about Canada. So why don't we turn our focus to Europe? And for the next question, perhaps Helen and then Odd could weigh in here. So you've been designing and developing 25 kV rail systems for generations. So from your experience, what are some of the typical pitfalls to avoid when creating that sort of AC system? First to Helen. Oh, Helen is on mute.
Sorry. Yeah. So basically, EMC is a wide range of consideration. What Prof just mentioned about EMI interface with enabling concerning the EMF, like the risk arising from physical agent, is only one element. So basically, following the best practices from design stage is very critical. So they can eliminate many common EMC problems. But for every project, I think it's different. Thus, the EMC issues can be very different, but mainly from our perspective, because Andy just mentioned they are considering the airport interface and also the utilities close to the railway. But for our rails infrastructure in the UK, I think we have the interface and have the best practice, so we have less EMC issues. But in terms of the electrification project, we did have some EMC problems. Many of them are within the railway boundaries. So the interactions among subsystems could go badly wrong. For example, during the train commissioning testing stage, and we found that it caused problems on the telecoms or signaling problems. So that would be like a majority of our work, not say on the interface with external parties, but surrounding with the railway systems.
Right, and over to Odd. Did you want to add to that question?
Well, I think a lot of subjects are already meant by everybody. I think what happened in the Netherlands was that we had a problem with a parallel line. We had a high-speed line, 25 kV, and a parallel line for a conventional rail with 1500 volt DC. And there we had some problems, although there was well looked at in the design phase, we still had some problems when starting operation on the high-speed lines. And the years directly after we opened the line, we already started with building additional auto transformer stations to avoid further interference with the parallel line, DC line, the conventional line. So at the start we had some problems. But what I want to mention further, I was for 8 years manager operations and now chief technology officer. In the last 9 years, we have 0 subjects about EMC. So if you design it properly, then you can avoid a lot of problems. And we don't have any EMC issues the last 9 years long I was manager operations and chief technology officer. The other thing I want to mention is earthing and bonding is very, very important. And later on, I will mention that also in the panel discussion that earthing and bonding is for all the infrastructure elements. That means also for the track, buildings, and so on. In a 25 kV situation, you have earthing and bonding is essential, but also for all parts of the railway line and the buildings. And well, I think I think that's sufficient for this question.
Okay, all right, we've got about 30 minutes left, so let's break this topic into 3 parts: design, construction, and operation. So starting with design, we learned that it's important to consider as much as possible electromagnetic interference and compatibility issues already in design. So how can we ensure these systems are safe and also are well designed? So on this one, why don't Helen perhaps, and then Odd. And Helen, you had unmute, please.
Should remind myself about unmute. Yeah. So understand the railway environment is very important from the design stage. One of the elements is the third-party interfaces, and also the compatibility among subsystems are very key. For example, when we're considering about the external to the railway, does the electrical clearance, as we mentioned before, between the new overhead line system and the existing infrastructures, either it's buildings or tunnels or bridges or footpaths, is a significant concern, because in the UK we have very conventional builds. And then they are very, very close to the railway, especially like footpaths and old railway buildings very close to the railway lines. So this is definitely, we look into that, and also to define the demarcation of the railway boundaries is also very, very important. I think it's generally accepted, like within our railway boundary, like 3 meters to 10 meters, or beyond 10 meters, we have different categories to do the assessment. So we have different considerations. Obviously, nowadays we have like other considerations beyond, like close to the railway, like from the radio frequency point of view, becomes an issue, and we always look into that as well. For all these things with external parties, I think desktop study survey give us very, very good information, the baseline, what should we do? And then we need to identify the key or the more significant like interface we need to look into from the beginning. And also in terms of the intrasystem compatibility, so we have a lot of to work on by ourselves, not necessary to the public, but they are very, very important to ensure everything goes well when it is in when we move on to the next stage. For example, so do we have a vision of the characteristic of the trains, whether they will be able to fit in very well with our electrification system? Because we do have some experience, like got some issues. And also we need to consider any requirement will be imposed on by the grid power supply network. In the UK, we do have some interface. We need to make the agreement with what kind of power we are taking and what kind of emissions we might emit to the network, to the wider grid system, so on and so forth. And also we have to consider the electrification system's impact on the existing rolling stock already in operation as well. So basically that is a bigger picture from design stage.
Okay, thank you for that. Add something to comment on.
Yes, what I want to add to what Helen told is that as soon as you did all these studies and all the stakeholders and you see all the interfaces and so on, as soon as you start with designing a 25 kV railway system, but a railway system generally speaking, for us was very important with the high-speed line that you use system engineering. That means that you have very clear and good requirements. And then you can use with system engineering. There's a specific standard for that, that you can do verification validation phases. And with that, when you have a good process, then at the end, you have also testing, commissioning, and so on. So if you go properly through all these stages, then you can also, then you can reduce the chance that you make mistakes. I think also important is that you bring in not only advisors, but also industries, because the high-speed line south was built by Siemens BAM and Fluor Daniels, and they have a lot of experience themselves with building these lines, and they can help you to improve also the requirements, that they are complete, that they are practical, because you can, of course, write a lot of requirements down which are not practical, and also the industry can help to avoid pitfalls. They have a lot of experience. So that's what they also want to bring in. And well, I talked already about the earthing and bonding plan, of course, that's important. But I want to add, well, keep to use system engineering, make a safety case, of course. There are standards for that. Bring in the industry with advice, and look at that you have good requirements to start the whole process for system engineering.
Okay, I think Andy wanted to jump in on this question.
Yeah, as our keynote speaker mentioned, the majority of the impacts from EMI impact the railroad itself. And if you're building an electrification system over an existing railway, one of the things you got to consider is whether it's going to be compatible with your existing signal system. What most people might not, if you're not in a railroad profession, what you might not realize is the same tracks that carry the train also are the backbone of the signal system and become the backbone of the return system for the traction power system. So when you go to overlay a traction power system into a railroad application, you got to make certain that your signal system will be compatible. In a lot of cases, it won't be. So then the signal system needs to be upgraded. Some of the options to do that are making them so that the frequencies are compatible. Other options is more modern signaling systems use CBTC systems, but they stop using the rails for the primary communication within the signal systems. But in all cases, when you're coming at this from the design perspective, you need to do the analysis up front to evaluate what those frequencies would be, and to try to determine at the design phase whether there would be interferences otherwise, and then they have to be mitigated.
Okay, and Andy, just stick with us here, and we'll come to you on our next question, and then Menno. So thinking about GO Transit, what are we doing here to ensure safety, especially in terms of EMC?
So I think Menno's still having audio. Was that directed to Menno?
Well, we'll start with you, Andy, you're on, and then we'll go to Menno in just a minute.
Okay, I'm going to touch on a couple aspects very quickly. We talked about the clearances, which we are, that's one that is probably first and foremost. The bonding and grounding also applies into that. When it comes to EMI, the first thing we've done is we've conducted studies to go out and evaluate what the existing system is. What type of naturally occurring EMIs and EMFs are around the railroad. As the professor's presentation showed, there's a lot of sources that generate these fields. From that perspective, then, we now have what we call a baseline. We did evaluations from environmental impacts to determine whether or not electric railroads would be impactful, and then what would the mitigations be if there were impacts. We are now at the design phase of this RER program. So we've put into our requirements for our contractors that they need to design a system that would be compatible with the surrounding area. So then once that is done, they'll submit those for review. But when that's done, we'll go back out when the system's built. We're going to go back out and measure again and determine whether or not they truly did mitigate any impacts that would be coming from the inclusion of the electrification system. And if it's not, then we have additional work to do. But as most people can, I think, accept, electric railroads are used throughout the world. So none of these are showstoppers. There are mitigatable elements.
Thank you. And we'll go to Menno as well.
Yeah, I'm back up here. Good. I hope the audio is also fixed. As the previous speakers and Andy has outlined already, from our perspective, we've looked at an integrated approach early on in the program. And it includes a systematic process of identifying the most appropriate system for the heavy rail application, which is the ATF configuration, extensive modeling of EMS emissions through operational simulation of the concept system, as well as analysis of an assessment of risk at sensitive receptor locations throughout the network. As Andy has alluded to this, we've implemented pre-programs to install provisional and passive protective measures, such as grounding and bonding at stations, as well as requirements, developed a standard for the installation of these elements at any of the future to be built structures and projects that we have in flight. We've also done extensive analysis of adjacent and overhead utilities, including commissioning an advanced relocation program for utilities of high risk. Alongside that as well, we have done extensive work in all the stations with respect to the placement of OCS, an assessment of the clearances and how the clearances affect adjacent and overhead structures throughout the system. And overall, from our perspective, and this is in our partnership with Gannett Fleming, we've sought to follow national and international guidelines and certainly adopt industry best practice with respect to control and mitigation of EMI, EMF impacts. And that includes requirements for the proponent to demonstrate mitigation through design, undertake the progressive field testing and verification under actual operating conditions to verify compliance with the requirements, and ensure that we maintain safety throughout. And from our perspective, we've also done a lot of work with our external partners. That includes the utility, HONI, as well as the regulators, to familiarize and to start the conversation very early on. It's taken us several years in that conversation with respect to the power connection process, as well as the load flow studies, power quality studies, and the like. In addition to that, we've had extensive conversations with the Greater Toronto Airport Authority, which is an area of assessed higher risk, and have requirements in the contract for the contract to demonstrate again mitigation and develop their design to ensure that effects and impacts are mitigated during this phase. As Arthur has already mentioned as well, these are the most critical parts, and in that early on phase, we've certainly sought to ensure that the contract is required to do so and is required to demonstrate to us how they are going to achieve that, how they're going to achieve that requirement.
Got about 20 minutes left, so we'll keep plowing through the questions. I do have an audience question as well I'm going to work in here. So the next question, though, is for Helen. And based on your experience, how far can the design of a system be when comparing to what you end up measuring once it's in operations? Once it's operational, excuse me.
Right, okay. So basically, it is a staged work. So measurement is actually embedded in all stages, even from the beginning, for products and components, like lab testing and gathering evidences from the product acceptance point of view, has already started, I think, from the design stage. Because in our REL, in the UK, we have like 8 grip stages. From the very early stage of planning, and also up to grip stage 4, we call it stage 4. We have the design, and actually we have already accumulated a lot of information. If it's not first-hand measurement, but we already started like testing. And also if you are introducing a new product, so we have another in parallel to any like electrification project or any other project. It's like from product acceptance point of view, because that takes very long in parallel to our constructions. And then we, until to that step, we have already have some basic understanding of what we are going to do. That is only the component, equipment, etc., but it's not the system. So the next step, obviously, is about the electrification commissioning testing. That will be a very big step, like to integrate the whole system, make it work. And then we have to check not just the electrification system. Obviously, that is the foundation, as I just mentioned, earthing and bonding, and also all the installations being in the right place. But still, we might have some issues from measurement to identify. Not necessarily it's all because of the design. We did have one issue. We have an adjacent area when we do the commissioning testing, and we notified some interference at the adjacent area. It's not the commission area. All these kind of issues is via measurement and can be mitigated. And eventually, I think majority of the system will work as intended. So that is the good thing. But there's a very, very difficult bit, is the train interaction with the overhead line system or the traction system. This is difficult. Although we do some modeling work or predictions, but when you put two things together, and that is a big kind of challenge for us, for some of the trains, because of the, should I say, in many early considerations of the emissions to the network, we have less issues, but in certain situation, we did have some mismatch. When we have the electrification, we have issues, but eventually, obviously, we can find a solution and then to get back to what we designed for.
I think Menno wanted to jump in here, maybe just a 30-second addition. Go ahead.
Yeah, Marco, thank you. So Helle brought up a very good point with respect to the impacts to the rolling stock. What we've learned over the years from Metrolinx as an agency that is developing this program with technology that it has not operationalized yet, is that the impacts are mostly within the right of way. Closely adjacent, parallel utilities are another high risk aspect that we need to consider. But again, in all the speaking aspects, including the professor, it's evident to us that again the effects are mostly within the right of way and mostly pertain to railway equipment. Whether it's signal systems to adjacent freight rails, Andy has just identified, and for which you can implement mitigations that may require replacement of equipment or other immunization type activities. Thank you.
Okay, thank you. So we'll talk a bit about construction and testing here. So a question for Odd. Now that we have a design system, we have to build it to spec. So how has your experience been with constructing these systems from an EMI, EMC perspective?
Yes, what you see is that for the high-speed line, I was in the construction of the track. So I was construction manager for the ballastless track on the high-speed line south. That was around 2002, 2004. And what you see, generally speaking, is that there was a lot of checking and testing done according to the design and the requirements, and measurements, magnetic fields that were measured, currents that were measured, and so on. But it started already, by example, if you construct a track, then the whole reinforcement of the track, there was a ballastless track with concrete and reinforcement. That was all connected to each other. There was earthing and so on. That all has to be checked. So it's not only that you say you measure magnetic fields and so on, but you also have to check is, by example, if you have a piece of concrete with reinforcement, is the reinforcement goodly connected to the earth? So this type of testing is done. But as soon as you have commissioned the system and it's working, I must say after that, there was hardly any measurement done. At the moment, the only measurement we do for the high-speed line is measuring the currents and the voltages. With the currents we measure because we want to know what if a new timetable is introduced or new trains, what is happening. We also look at the impact of the switches, especially if there's interference with the electronics in the switches. And that happened once. And that's are the things that you look at. But during the construction phase, all systems has to be checked on their specific sub requirements, you can say. So you have general requirements, and you divide, you detail out the requirement to all of the structures, and then you might have certain structures that you have to test or that you have to check or to inspect.
And just a question from the audience, thinking back here, when you were talking about rail platforms, did you find locating local communication systems using copper Cat6 running at canopy height caused issues? And is there any benefit to running main communication runs beside platforms where it's possible? So devices like speakers or cameras, that would need to be at a higher level. Perhaps a brief answer on that. And also, would there be benefits to using Cat7 cable shielding or above?
The thing that I can mention, we have done a lot of shielding of cables, especially in switches and so on. So that's, I cannot say it for platforms. Maybe Helen can say something about it, because the high-speed line south is not going through stations. So it's we have voltage changeovers to Rotterdam and to Amsterdam. That means that the high-speed line is only between the cities, and there are no platforms on the 25 kV part. So maybe Helen can answer that question better, I think.
Okay. Right. So we actually have like it's not generally happening everywhere, because the design already have considering where we lay our 25 kV, either positive or negative cables or overhead line or the ATF cables. So basically, if you are just put your one cable as from the professor's description, if just put one cable very far away from the other one and it carries a very, very big current and it's just underneath the platform, and we might need to consider these kind of issues. Otherwise, I say in many situations from the design stage, we have already eliminated this. But in terms of other sensitive devices, it is very, very much depending on what kind of device we are talking about. And then we will look into that on a specific cases if we do have any considerations.
Okay, all right, let's talk a bit about operations. So assuming the system, I think I maybe asked that one, but no. But assuming the system's built, there still are some EMC issues present. So how do you mitigate those post-construction? So it's over to Helen and then on.
Right, okay. This is very avoid the situation or challenge on EMC. So basically, I think any mitigation or any from design stage cautious be made, as Ed just mentioned, we still might have EMC problems. So when an EMC issue comes up, you need to have a kind of victim or something's being affected. So that is a bit more specific than a general case. And then we need to we carry out a technical investigation. So me and my small team or in the central function, we support the investigations in this situation. And that will involve all relevant parties, because it's not necessary just for EMC can solve the problem. And also we need to do additional testing to identify the problem more clearly, and then to do the measurement and give us the quantified measure, say what the severity and what kind of options we could have. But in many investigation, I think it can be mitigated after all these investigation. But in extreme situation, if we need to do the modification on the train or on the signaling system, or doing copper cable replacement with fiber optics, or install filters or reroute cables, etc., can all be, I think, they worked out to find the best option for all parties.
Do you want to add anything briefly?
I want to add. I think that's completely. There's a complete story Helen told. Yeah, you have normally and when you have a problem, you analyze the situation, then you do a course analysis. What is the course of it? And then you come with possible solutions and you implement them. So we have a technical change process for that. So as soon as you know, well, we might have a technical solution, then we have a technical change process. It might also be the case that you change procedures. We had an interesting case a few months ago where we had new antennas for the mobile phone network in tunnels. So we have all the tunnels are equipped with antennas for using mobile phones in tunnels. It took a long time before that was decided and paid by the state. But now you can finally use your mobile phone also when you go into a tunnel in the Netherlands. That took a lot of time. But the special thing was that these antennas have a lot of power and high frequency. And there was a risk for track workers then at that moment when the antennas were brought in the tunnels. So there was not a simple solution for that, but the solution is a process type solution. You have to keep a certain distance to the antennas, and if you want to do the maintenance work close to the antennas, then we have to change them off. They have to switch them off, the antennas. So we have to deal with every problem, and it's always the same situation, course analysis, think about possible solution and implement them. And that's a normal technical process, a normal process.
Okay, quick question here from our audience. So it's a jump ball, whoever would like to answer. Go right ahead. We'll keep it brief so we can get through a couple more before we reach time. So question is, can you briefly describe some EMF mitigation when DC and AC systems are running parallel?
I can answer that because we had that issue in the Netherlands, of course, in the northern part between Rotterdam and Amsterdam, and also in the southern part. At least what has been done is that additional auto transformer stations have been built, so that the interference with the other line is less, and also there were some modifications made on the conventional line with let's say bringing in how do you call them, condensators or whatever. At least that for AC there is an earthing with the soil, and for DC not. So there was some additional modifications done on the conventional line also, but I must say it cost a lot of money. So you can better look at front if you have enough AT stations. So and check it at front. And I must say it was a little bit strange that this additional AT stations had to be built after commissioning of the line. So there's I think more to tell there, but not for an audience.
Yeah, there's multiple instances where AC and DC systems actually run on the same tracks. Long Island Railroad comes into New York City and uses Amtrak's lines, so the two systems actually integrated together. And yeah, there's some precautions that have to be taken. The bigger one actually is not EMI related; it's really corrosion control, and because the DC systems interact with the AC systems in terms of return circuits, so that becomes a bigger issue in terms of making certain that they're protecting the equipment electrically, so you don't get the stray currents and return currents coming onto paths you don't want them to go to.
Yeah, I have one something to add up from our experience in the AC/DC, like close to each other, the area. Obviously, probably the question is not about AC/DC changeover. So we have AC/DC changeover in the UK, and also for the AC/DC close to each other areas, they running separately. Even we have the separation, as Andy mentioned, we will have the stray current issue, and we did observe. I think probably back to now we have some like enhancement in terms of the DC return current back to the substation, but at the early time we did have some like very bad examples of our overhead line structure burst because of the corrosion like happened on our like structure metal component. So this is a very, very important part we have to consider. That is in terms of the DC operation. But for the AC operation, I think this kind of stray being mitigated in many ways because we have return wires and we have APF rails, and also enhance the area earth wire, etc., to link to try to let the AC current return back to our substation more easily rather than the DC.
We've got 2 questions to go, and then we will be at time here. So let's have brief answers so I can squeeze them both in, and maybe even check the audience one more time. So thinking about typical processes through the lifetime of operations in your systems and measuring and accounting for interference, taking into account changes in the environment, what are some of the processes that you go through? We'll start with Helen and then go over to Odd.
Right, from an EMC point of view, basically I think EMC is a live subject. So we cannot say once we have completed the construction and things are over. So from our practice point of view, we have the EMC strategy at the beginning for the project, set up the high level requirements. And also we have another very important part, we call it EMC project file or project files. So this is actually it's not a file itself. It contains a suite of documents for management, test plan, test reports, and verification reports. And also to the later stage, we need to have the acceptance document and also handover document. When we hand over the project to the maintenance asset management team, and then if there's any like risk is still open, or if any EMC considerations need to hand over to the maintenance team, and they will carry on. And also, I think from the Infraspeed point of view, just mentioned some experience of new installations, because technology always develop and the demand on the infrastructure manager is never ending. And then we need to have new installations. And so modifications, changes always like need consideration of EMC.
Yeah, if you look how we work with Infraspeed is that if you have new installations or modified installations, then you always first define the requirements. So you take the old requirements and maybe new requirements, and you put them on paper for the new installation or modified installation. Maybe you have a little bit easier situation is that for let's say electronical parts, because the line was built by Siemens and Bohm, we always go for electronical parts for Siemens. They take in the requirements and they make a design and also deliver the documentation and the certification that it's that also EMC is covered. So the whole certification and everything is done also by the supplier Siemens to us. And then it's simply often also constructed by them or installed by them. And then we also get the complete technical file. So it's again, it's the same. And if it's not like in our project, it's always the same. You have requirements, and then you go down to design, installation, and verification, validation, testing, and you certification, and then you get all your documents back, and then you're finished. I think if you look at constructions or buildings outside the high-speed line, then when they're in a specific distance of the high-speed line, there always has there's a law that says that they have to come to the asset manager, and we have to discuss with them what are you doing, where might there be influence from your new building to our high-speed line, or our high-speed line can influence your building. So, and then we start also the discussion with parties who have construction work outside the high-speed line. So that is also a well-defined process. And well, we have now in the north of Holland, we get new we will have additional, we will modify the highways, the motorways. So there we are already 5 years in advance discussing with them what are they planning. They will change the aqueducts and so on. So already 5 years in front of that modification, we already are in discussion with the state and the construction parties.
Thank you. Okay, so let's talk about standards, and then we'll have time, I think, for an audience question here. So this one is for Benno and for Andy. Having gone through design and environmental design, recently, do you assess the standards available today as sufficient to guide an organization through the process?
There's a couple aspects of this. CSA provides a lot of guidance with terms of protection to the general public and employees, and so those guidelines are generally sufficient. In some instances, and Menno can touch on this, we've actually engaged with CSA to either update or bring certain specs into consideration of an electrified 25 kV AC electrified railroad into Canada. Other guidance is very common. There's a lot of synergy between European specifications and North American specifications. Matter of fact, they've more recently they've been working to make sure that those are compatible to allow for basically global trade. The manufacturers aren't always located in your country where you're building a railroad. So we want specifications. The industry's work to make the specifications universal throughout the world, and that's really helped us. Now, I think we're at a better stage now in 2021 than we were even 15 years ago with that standardization of specifications. Menno, do you want to add to that?
Yeah, you've already mentioned this, Andy. We've certainly reached out to CSA, other industry and non-industry stakeholders to continue to develop and enhance the standards within the local Canadian context. And we will continue to do so as we progressively build the electrification program. And as Andy has mentioned, we are certainly looking at the international wider industry, and again, adopt that industry best practice approach. On the other, in another aspect here, for Metrolinx, we are also developing in-house engineering and asset management expertise and competencies to build that capability alongside our realization of these types of assets, so that we can continue on this this assessment of EMF impacts, as Helen has alluded to. This is not a silent subject. This is a constantly active subject, and we're certainly building a level of expertise with the agency to be able to continue to engage with our affected parties and external and internal stakeholders.
Thank you. All right. We have an audience question. I'm just finding that here on my screen. I just had it, of course. Just bear with me. Here we go. Okay, a malfunction of protection relays occurred during commissioning of a new 25 kilovolt line, and the problem was resolved after changing the grounding connection of the switchgear to a more direct link. Hence, earthing connections could pose an EMC issue and should be part of the EMC study. Similar interference occurred to the signal system. Who complained the interface signals came from the common grounding installation. Should the grounding of the two systems be separate or commonly bonded? Anyone can unmute if they'd like to take that question up.
Well, I'm going to just throw out one soundbite real quick. While that's incredibly important that the earthing and bonding, or bonding and grounding, whatever term you want to use, be considered with EMI, this issue has more to do with bonding and grounding than EMI mitigation. And there's a philosophy that has to be adopted by the operating railroad on how they're going to drive their EMI and their bonding and grounding work. And the consideration has to be, are you going to bond for and protect for your equipment, or are you going to bond for and protect for your worker safety? Because in some circumstances, the two aren't compatible. You can protect your equipment, but you create a health issue, a risk issue to your employees. In other cases, you can protect your employees, but then you're sacrificing your equipment. So without going into a lot of detail, because it's a whole nother conversation to get into, I just need to put that out there. But in most cases, I would suggest, though, to answer the question very simply, separating the bonds, the grounds is the better prudent way to go.
Any others want to jump in or answer? Okay, so we're a couple of minutes over, but I know we had some audio issues at the beginning. So Menno, it's very important, the Go Electrification program, certainly. So I just wanted to give you an opportunity, if you wanted to give a very brief summary of how your experience has been so far in terms of dealing with EMI, and then I'll pass it back to our hosts.
Thank you for that, Marcos. Very briefly from my end, it has certainly been an extensive learning process for the agency, as I mentioned, trying to operationalize assets that we aren't familiar with. The whole journey and experience with EMI is, again, looking at industry best practice and international experiences. It is an aspect that is recognized as a risk, and can be effectively mitigated in design throughout. And there's many mechanisms and ways that we can actually manage and mitigate and control EMF. So it's a great learning experience, and it's been a pleasure to hear the other panelists as well and sharing their experiences as we continue on our journey to electrify the Go network. Thank you.
Okay, thank you. And thank you very much to our panel. Thank you to Andrew and Helen and Menno and Odd. Really appreciate it. A very enlightening discussion. And so with that, this will conclude the panel part of the program. So I'll turn things back over to our hosts over to Jasmine. Thank you very much, panel.
Thank you, Marco, and I'd like to echo the same sentiment. Thank you to our panelists. Thank you to Professor Razai Zare for a very great presentation about this topic and for an awesome way to start off the discussion today. I'd like to share a quick slide with all the attendees today as well. There we go. Hey, I'd just like to mention to everyone that if you enjoyed today's presentation, that OSPE as an organization hosts multiple webinars that are free for registration for our membership multiple times a month. The next coming up webinar is on technology disruption and future-proofing your business around that. It is being held next week on the 28th at 12 to 1 Eastern Time. And the one after that is on digital seals and the future of engineering. Again, a free webinar for OSPE members being held on November 3rd, 12 to 1 Eastern Time. OSPE additionally has some career services that are free for OSPE membership, including a virtual engineering employment event. So if any of the attendees in the presentation today would like to attend this, our next event is for October with a deadline for registration at the end of this month as well. If you have any questions, I'll be leaving my email address in the chat, as well as the contact information for our partner today, Felipe at Accio, in the chat as well, if you'd like to ask any questions or if you had any other inquiries. Thank you so much to all of our panelists. It was a great discussion, and I hope that we can do something collaborative again in the future.
Thank you.
Thank you.
Thank
Have a
you.
good day.
Thank you.
Thank you very much.